How is it going, everyone? My name is Ryan Baldwin, and this video is going to be on carbon dating. I've listed out here a few learning objectives, so things that I hope you learn as we go through this video. The first is, what is a half-life? What are we even talking about when somebody mentions a half-life of an element or an isotope? Second, what is carbon-14, the radioactive isotope of carbon, and how is it incorporated into living tissue? So how does it go from being in the atmosphere to being inside your body? And third, how are half-lives used in techniques like carbon dating? First off, we have an equation that we'll use for an example problem later in the video, but I wanted to go over this equation so we could think about it as we go over what half-lives are and how they're used in carbon dating. So in this case, N is equal to the amount of radioactive isotopes that we have after a certain amount of time, with N naught being the amount of isotopes that we started with. E is the base of the natural logarithm, and lambda is the decay constant. Down here we have the reworked decay constant for a half-life. So now, what is a half-life? A half-life is a statistical property of a radioactive element or isotope. Radioactive elements or isotopes are unstable and will, over time, decay to a more stable state. An example of this is uranium. Uranium will go through 5 different processes called beta decay, where over time uranium will decay all the way to lead. Now lead is a more stable state, a more stable nucleus, and the nucleus of uranium will no longer decay. So once a uranium nucleus has decayed all the way to lead, it's happy there and will stay there. So now we're going to talk about this in terms of half-life. So over here I have an example problem. So if we had 1,000 radioactive particles and its half-life was 100 years, which is a pretty fast half-life, that means that after 100 years, we expect 50% to be remaining. Meaning, if we waited 100 years, if we've been watching these particles for 100 years, and then we measure again, we should only see 500 radioactive particles. This means that 500 of those radioactive particles actually decayed to their more stable state. The 500 that we see are still in their unstable state. Now, after another 100 years, so a total of 200 years, or 2 half-lives, we'd expect to see 50% of our 50%, or in this case, 250. This means that we have 250 radioactive isotopes remaining, and 750 of those radioactive particles decayed to their more stable state. Now, what would happen after 1,000 years? This would be 2 to the 10 half-lives, meaning that after 1,000 years, we'd expect to see 0.977 particles. This means that after 1,000 years of our 1,000 particles, we expect to have about 1 remaining. In this case, in this thought experiment, obviously the half-life of uranium is not this short, but in this case, if we started with 1,000 uranium particles, and then its half-life was 100 years, after 1,000 years, we'd expect to have barely not even 1 remaining. So, what is carbon-14 and how does it get into our body? It all starts with the sun. The sun is sending out high-energy particles that are going to collide and mix around and hit things in our own atmosphere. One of the things that gets sent out by the sun is a neutron. This neutron is going to come in and is going to collide with a nitrogen nucleus inside of our atmosphere. Now, nitrogen normally has 7 protons and 14 atomic mass units in its nucleus, meaning it has 7 neutrons. So 7 protons and 7 neutrons for a total of 14. When that high energy neutron collides with our nitrogen nucleus, we are left with still 14 because it replaces itself with that proton, but now we only have 6 protons, and so this nucleus is now a nucleus of a carbon atom. And then it's also going to emit that proton, which is actually just a hydrogen ion. Now, this process is happening at a known rate inside of the atmosphere. This means that not all carbon inside the atmosphere obviously is this radioactive isotope, but just some of it. And this happens in a known ratio. So in our atmosphere, we have 1.3 times 10 to the negative 12 carbon 14s to every 1 normal carbon, which means that carbon 14 is relatively rare. Now, this carbon 14 is in the air, and it will act just like normal carbon. So carbon will react with oxygen to form carbon dioxide, and that will go inside plants during photosynthesis. Now, these plants are going to use that carbon dioxide to create things like an apple, and you are going to eat that apple, and the carbon is then going to be deposited in things like the bones. So this is how a radioactive element in the atmosphere can go inside of your body. So that means that at any given time, as long as you are eating plants or eating something that eats plants, then a fixed ratio of the carbon inside your body will actually be radioactive. So we can apply that concept to something like carbon dating. Carbon dating is a mathematical process of measuring the amount of radioactive isotopes in a sample and then determining how old that sample is. So we're going to do an example problem, and we're going to say that we have 3.5 kilograms of carbon. Now this could be, let's just say this is a bone that we dug up in the ground. It's a 3.5 kilogram hunk of bone. So first off, what we're going to do is we're going to find out how many carbon particles are in this 3.5 kilograms. So we're going to do some conversions real quick. So in 1 kilogram, we have 1,000 grams. And in 1 gram, we have, in 12 grams of carbon, we have 1 mole of carbon. And in 1 mole of carbon, we have Avogadro's number of particles of carbon. This works out to mean that we have 1.76 times 10 to the 26 carbons. Now that's a lot of carbon. So using that fixed ratio we said from earlier, 1.3 times 10 to the negative 12, we can multiply that by this number that we just found to find out how many of those carbons that we just found in our bone are actually supposed to be radioactive. And that comes out to 2.28 times 10 to the 14th carbon 14s. So that means that in this 3.5 kilogram hunk of bone, there are 1.76 times 10 to the 26 carbon molecules, and 2.28 times 10 to the 14th of those are actually radioactive. Now, if we measured this and we found that we actually only had 80% of what we should have had, meaning n over n naught, so the amount that we have now, or the amount that we had initially, is equal to 0.8, we can use that equation that I showed earlier to figure out how old our bone is. So we can take 0.8 is equal then to e negative lambda t. We can take the natural log of both sides, and we get negative 0.22314 is equal to negative lambda t. So if we solve this for t, then we get t equals negative 0.22314 over lambda. And I showed you what lambda is at the start of the video as well, which is equal to 0.693 over half-life. Now we know what the half-life of carbon-14 is, and that half-life is equal to 5,730 years. So in total, if we write this all out, then we have negative 0.22314 over 0.693 over 5,730. And this will all come out to 1,845 years. So this means that if we know how much carbon we have in an object, we can calculate how much of that should be radioactive. When we actually measure it and we come up with an actual value, we can use this equation to find out how old something is. The reason we can do this is because if you are no longer eating anything, so you're obviously dead, so that means that the carbon-14 in your body is no longer constantly being replenished, and so when you die, you have a fixed amount. So obviously this won't be especially since half-lives are a statistical property. We can still use this technique to tell very accurately how old something is. So now, why does this matter? Carbon dating is an important application of physics concepts that allows us to tell how old things are. The things that we discover through using this technique can tell us how old things are that we dig up from the ground, so archaeology, and they can be used to tell how old artifacts are or how old something is that has been dug up, just in general. This is a very applicable form of physics, and I hope that you learned a bit about how we can find out how old something is mathematically through using the concept of half-lives or the fact that radioactive isotopes or elements will slowly decay over time. I hope you enjoyed this video. I hope you learned something, and best of luck studying.